The topic of research is keystroke dynamics recognition using an 8-variate prediction ellipsoid for normalized data with a reduced feature set. The authors are Sergiy Prykhodko and Artem Trukhov. Keystroke dynamics recognition is a prominent technique in behavioral biometrics, offering continuous and non-intrusive user authentication based on individual typing patterns. It leverages temporal features such as key press durations and inter-key latencies, which are distinctive for each user. A low accuracy in keystroke dynamics recognition can negatively impact security, convenience, and personalization. Therefore, despite the variety of existing methods for keystroke dynamics recognition, there remains a need to continually develop and improve these techniques. Keystroke dynamics recognition has improved a lot recently, with various techniques developed such as linear discriminant analysis, tree-based models, support vector-based methods, principal component analysis, combined with k-nearest neighbor, neural networks including convolutional and recurrent neural networks. However, in the context of keystroke dynamics, one-class classification is more frequently employed. It builds a model based on a person's unique typing patterns, focusing only on their data without needing samples from others. This is commonly used in authentication systems where the goal is to confirm that the current user matches the stored profile. Similar to outlier detection, it checks if new data fits the profile and flags anything unusual as a possible anomaly. Among the common approaches to one-class classification, prediction ellipsoid and machine learning methods, one-class support vector machine, isolation forest, and autoencoder. Numerous methods used in keystroke dynamics recognition rely on the assumption of a normal distribution of features, which may not always hold. Enhanced mathematical models to better accommodate deviations from the multivariate normal distribution can lead to more accurate systems. The study addresses this challenge by applying normalizing transformations that aim to adjust keystroke data toward a multivariate Gaussian distribution, thereby aligning more closely with the assumption of statistical recognition models. Normalization techniques encompass various approaches, including univariate transformations that operate independently on each feature. In contrast, multivariate transformations consider the correlation between features, offering a more comprehensive adjustment. The study uses the CMU keystroke dynamics dataset, which contains detailed typing data from 51 people. Each person typed the same password. The dataset includes timing features, such as how long each key is held and the time between key presses, measured in seconds. In this study, a reduced subset of 8 features was selected to create vector X. The features represent a continuous segment of the password near its end and include both hold times and inter-key latencies. The selection captures individual key behavior and transitions between keys, providing a compact but informative representation of typing patterns suitable for multivariate modeling. After extracting features vectors, the next step is to find and remove outliers. One commonly used method for outlier detection is based on the squared Mahalanobis distance. The table shows the squared Mahalanobis distance values and the indices of the outliers that were removed. Equation 1 shows the 8-variate prediction ellipsoid. The left side is the squared Mahalanobis distance, and the right side is the chi-square distribution value based on the number of features and the chosen significance level. In cases where the raw data doesn't follow a multivariate Gaussian distribution, normalization is first applied to approximate multivariate normality. After this step, the 8-variate prediction ellipsoid for the normalized data takes the form shown in 2. Normalizing transformations can be categorized into univariate and multivariate approaches. The box cross transformation generalizes adjustment through a power function parameterized by lambda. The transformation is defined as equation 3. The univariate box-Cox transformation is applied element-wise to each feature. When dealing with multivariate data, this transformation is typically applied independently to each of the k-features, resulting in key-separate transformations. Maximum likelihood estimation is commonly employed to identify these optimal parameters, using log likelihood function 4. While univariate methods can improve the separate distributions of individual features, they don't account for the correlation between variables. This limitation is addressed by multivariate normalization, particularly the multivariate box-Cox transformation. It requires the estimation of multiple transformation parameters by maximizing a multivariate log likelihood function, equation 5. In one-class classification where the goal is to separate target instances from anomalies, common evaluation metrics are specificity, recall, precision, F1 score, and accuracy. Accuracy acts as a gauge for overall correctness. Precision quantifies the proportion of samples predicted as target that are indeed from the target class. Recall represents the proportion of target samples that are correctly identified. Specificity highlights the model's capacity to accurately identify anomaly instances. F1 score is a harmonic mean of precision and recall. Table shows a comparison of the recognition performance among various methods, including the prediction ellipsoid constructed for non-Gaussian data, the prediction ellipsoid for normalized data using univariate decimal logarithm transformation, the prediction ellipsoid for normalized data transformed by the univariate box-Cox transformation, and the prediction ellipsoid for normalized data by the Eight-Variate box-Cox transformation. The results show that applying prediction ellipsoids for normalized data greatly improves recognition accuracy, recall, and specificity. While univariate transformations lead to noticeable improvements, the Eight-Variate box-Cox transformation provides the most accurate and balanced results, and it takes into account the relationships between features. This study explored the impact of non-Gaussian data and examined how the application of prediction ellipsoids for normalized data affects keystroke dynamics recognition, accuracy, recall, and specificity. A new reduced feature set was used consisting of hold time and inter-key time features. This combination reflects different aspects of user behavior, key press duration, and transition time between keys, allowing the model to capture more diverse typing characteristics and improve recognition outcomes. The results demonstrated that the application of prediction ellipsoids for normalized data significantly enhances the recognition accuracy, recall, and specificity. Among the evaluated transformations, the Eight-Variate box-Cox transformation achieved the most accurate and balanced results. This confirms the advantage of multivariate normalization, which preserves correlation between features and brings the data closer to a multivariate normal distribution. In contrast, univariate transformation, decimal logarithm, and univariate box-Cox showed only moderate improvements, and they treat each feature independently and do not account for inter-feature dependencies. Future research could expand the dataset to include factors like environmental factors, as well as extended key sequences to provide a more realistic representation of user behavior. The incorporation of alternative normalization techniques, such as the Johnson transformation, could further enhance model accuracy by addressing the impact of non-Gaussian data.